Ladies and gentlemen, I want to thank the organizers for inviting me to the session and for giving me the opportunity to discuss the use of solar EUV irradiance for modeling geospace. My talk revolves around thermospheric modeling, as much of these findings arose during discussions in a Living with the Star Institute team focused on thermospheric drag. I want to acknowledge Sean Brunsma, in particular, for educating me about the thermosphere and alerting me to the issues on the solar side of things. So let's start with a brief background on this topic. This is a chart developed during the discussions at our LWS Institute team meetings, and you can find details at the Zhang et al. You can see there are many pathways that affect the drag estimation. Some are from the ITM, and our concern, of course, here is the solar radiation ones that I mark here with red arrows. So there are two agents for that: the irradiance variation directly and transient effects from coronal mass ejections and co-rotation in the Russian regions. In the next chart, I try to summarize the impact of those effects on the thermospheric models. So here I have compared them in compare both short-term and long-term effects. For short-term, obviously, we have the CMEs and CIORs, and in terms of irradiance, the flare irradiance. And as you can see, the biggest impact, at least on density variation, comes from CMEs, about a factor of 8. Long-term, we have, of course, the EUV irradiance, which at the factor of 10 or so is actually the biggest contributor in thermospheric variance. And the geomagnetic activity, as I described, is a much more complex pathway and depends a lot on the particular conditions. And so I'm not going to discuss this. I'll leave that to further experts. So how this input of the EUV radiance is used in the models. Here I have a few examples of empirical thermospheric models. Of course, the EUV irradiance, as we saw before, affects the temperature and density of the thermosphere. And so one would expect that the irradiance spectrum will be the primary input. But as you can see, that's not the case. Instead, the models use a radio proxy, the flux at 10.7 or 30 centimeters, or a linear combination of other solar indices like magnesium 2, Lyman alpha, which I'll also discuss in a little bit. So why is that? I think part of it is historical inertia. EUV spectral measurements were not regularly available until at least 20 years or so ago. And they're subject to well-known deterioration in orbit of the instruments, the cross-calibration issues, which makes it difficult to build long-term series of the EUV evolution and to study climatological effects or test validate various modeling approaches. However, the radio emission itself has issues. The different wavelengths arise from different heights of the atmosphere. 10.7 comes from lower down than 30 centimeters, for example, and therefore the 10 centimeters may reflect more like diffuse emission in the corona rather than sunspot based emission that is reflected 10.7. Basically, the modeling of the thermosphere, complex as it is, already starts with a disadvantage. So it makes it difficult, at least in my eyes, to understand if poor predictions of the thermosphere are due to modeling gaps or bad inputs. And I saw an example of that later. And I believe we can do better. So here is, again, a top-level summary of how we can use EUV irradiance in the models. We have the classical and traditional way using the solar proxies, either radio or separate wavelength bands, either in the FUV or in the EUV. Or more recently, we can now look at images, full disk images in the EUV, or go back to the fundamentals, the magnetic field, and look at empirical relationships to create say a proxy for the EUV irradiance. And those two are the ones that I want to discuss further. But first, let's see how the solar proxies sort of fare. Here's an example from Sean Brunsma of the use of two solar proxies. One is from the ACM in red and the magnesium 2 in blue, and compared to the F10.7 all in converted to the same units, solar flux units. As you can see, all three of them give different numbers, and so it's not clear why is that, or which one is the best to use. One would think that the ACM, since it is a EUV channel, would be the best. So this problem is really what we discussed in our LWS team, and drove us to summarize our findings in a paper with Sean. You can see more details there. Here I picked some 4 more relevant findings. The big one, I guess, is that at the moment we cannot really do very well in forecasting the thermosphere. Maybe you can do it up to 3 days when things are quiet, but all models sort of revert to climatology after that. Some of the other issues that I found coming in from sort of the outside was that it was never a clear connection to me why we use a particular index. We couldn't understand exactly to what level of at what height of the atmosphere this was more relevant, or what was the more appropriate for the particular time scales concerned. Plus, we don't quite understand what are the physical processes that give rise to the variations in a particular index. Like I mentioned something about the radio, but similar issues or aspects reflect different wavelengths within the EUV spectrum. There are also issues, of course, with bookkeeping of the time indices, as I will say pretty soon. So let's see what we can do with images. Since 2010, we have SDO that gives us full disk imaging in 6 EUV channels, 24/7 at 12 to 24 second cadence. And the last couple of years, now we have an operational version of it in the form of the GOES SUVI instrument that has 6 similar channels at 1 minute cadence. So we know that this is going to be available long term, since this is an operational telescope, and therefore we should do our best to make to exploit that data, since a 1 minute resolution is capable for capturing both flare and long-term variations. So this is an example from Fontana et al. That may show us a way forward. What they did, they took the SDO images and the 6 channels, and they used information on all these 6 channels to segment the features into active regions, coronal holes, chromospheric features, and so on. Then they used physics-based modeling to basically use the area that each feature covers to create the EUV response, spectral response. And because the atmospheric models cannot really accept the full spectrum, they translated their results into typical indices used for the modeling, as you can see here, S10, M10, and Y10. As you can see, they're not quite similar to the variations seen in the indices, although overall the variation is quite similar. So the result was that this particular approach behaves at least as good as the F10.7 that you can see here in blue. In black is the Gaussian measurements, and in red the spectral synthesis results. And so it is a promising approach, but of course there are some issues, as you can see, for example, here in the In the S10 index, there is a very big disagreement between the spectral synthesis results and the actual index. When we looked into some of these other aspects, not this particular one, we found that some of those discrepancies arise from reevaluations of the indexes because new instrument calibrations become available that may not be very well recorded, or maybe not, the models may not be familiar with them, and therefore may use say older versions that can result in up to, as you can see here, 40% difference in the irradiance that is being recorded in those indices. More details in the paper, but this is something that you should be aware of. Now, the other approach, as I said, is to go back to fundamentals and the magnetic field in the photosphere. This is really the driver of all solar activity, CMEs or long-term solar cycle effects. And if we could understand the exact physics that allows magnetic energy to hit the corona and therefore create the observed EUV irradiance, of course, then our problems will be solved. We're not there yet. However, the use of the photospheric field has a big advantage. We can use flux transport algorithms like this DAP algorithm that is being deployed operationally to propagate the observations to the future, up to 7 days, possibly 3 days for sure. Something that we cannot do with the images in the EUV. Then, using a similar approach as Fontaine did with the images, one can segment the field and use empirical schemes to predict the emission in different band passes. And here are the examples for band pass close to ASEM, another at Lyman alpha. And as you can see, the forecast, even at up to 7-day forecast, is very close to the 0-day forecast, within 10%. So it is quite promising, even though it's still at a very early stage. And I believe that the combination of this approach with the approach using the SUVI images, which has a bit more physical information in it, could really help create a hybrid spectrum that could be maybe quite useful for short-term, say a few days forecast. So as I approach toward the end of my talk, I would like to give you a list of some of the bottlenecks that I found as I was doing the review. Of course, the obvious one is that the thermospheric models cannot use the full EUV spectrum, and I don't know to what extent this can be possible to improve in the future. The other approach, which I just discussed, is to invest a bit more in understanding the physical relationship between magnetic field images and physics, so that we can provide a bit more sophisticated EUV synthetic spectrum that will help in the long-term forecasting. Now, for nowcasting, I agree with Lilienstein that making measurements at a few key channels, one could reconstruct the overall spectral response, and channels like Lyman alpha, oxygen 5, carbon 3, as he says in the paper. Now, if we really want robust and a robust extension of the forecast horizon, well, we just have to make the measurements in other locations, and the obvious one is from L5, so we can see the activity that's going to come over the visible disk from Earth, deploying either these sort of simplified spectrometers that Lilienstein advocates for, or magnetograms will definitely help us expand the horizon to 3 or 4 days right away. And if we combining them with an adapt sort of operational model, we could possibly model the activity as it crosses the whole disk from limb to limb. And now in closing, I think there are 3 approaches that we should be aiming for in terms of improving the EUV irradiance inputs to photospheric models. Of course, the easiest one is to clean house. Basically, have clearer requirements, clean up the bookkeeping of the indices and their updates, and that will really help at least validate the different models. Obviously, we need to keep taking EUV irradiance monitoring. This goes without saying. And we already have that capability with GOES. But more exciting for me from a scientist's point of view is these new approaches that are becoming available, both using the images and the magnetic field in a fresh combination with a better physics-based modeling on the solar side to improve the irradiance monitoring and expand our forecasting horizon. So this is what I would like to say, and thank you for your attention.